And at the end, sorry, do I just turn off or do I
I'll end the feed.
Someone to...
Kia ora koutou, ko Douglas Walker, tōku ingoa. Really pleased this morning to have Jenny Pollock. Jenny's a very well recognised Earth and space science educator in New Zealand. Jenny, for a long time, has been president of Earth and Space Science Educators New Zealand and has recently taken up the senior vice president role. And so thank you, Jenny, for all the work that you've done across the country in that role over the years. Jenny's going to be leading us through the 2 external standards for Level 2 Earth and Space Science today. If you've got any questions, please type them in the chat. And one of our colleagues, Andrew Sargent, is going to be monitoring the chat, and he will either interrupt Jenny and ask any time-sensitive questions, or he'll collate the questions and ask them at the end, just depending on the nature of the question. All right, so without further ado, I'll hand over to you, Jenny. Thank you again for your efforts and your time today.
Okay. Kia ora katoa, everyone. I'm going to be going over the Extreme Earth Event Standard first, and then I'm going to be going over the stars and planets. There's not a lot of people sitting the third external, and so I'm not going to go over that. I think there's probably plenty of resource material available for that. So without further ado, I'm going to start on extreme Earth events. I do have what will seem like a very long PowerPoint, but I don't intend to go over it all. I have left, it will go into the shared folder that you would have the link for at the end, but the slides I have kept in that I don't talk to are really just enhancing what I'm going to particularly be mentioning. Before I start with the slides, just remember when you get the exam that each paper that you have 3 questions. So manage your time carefully. You do get 3 hours to do it in, so you do have a nice amount of time, particularly if you're aiming for a high grade. Be aware that with each question there also is a box in which you can put diagrams. And I have marked papers before a lot and have seen excellent diagrams that can also gain grades. So if you are good at expressing yourself diagrammatically, practice doing key diagrams like subduction of a tectonic plate and that sort of thing. And I'll point those out as I go. But main thing is to make sure they're very carefully labelled, very carefully annotated. Just a diagram won't get you any increase in your grade or anything like that. But so annotate it carefully, even explain and use arrows to link bits together, and you will find that your grade takes into account a well-drawn and well-labelled diagram. And good luck, everyone. I hope you do really well. Right, I'm going to start to share now. And so there's an hour for extreme Earth events, or maybe just 55 minutes rather, 57 minutes, then a quick grab a glass of water, etc. for me, and then I'll be going on to stars and planets. Right, let's get started. Okay, so hopefully you can see that all, and we do have someone who will tell me if we can't. So I'm going to start off with a very basic thing.
Have you shared your screen? Because it's not showing up.
Oh, is that not showing up? Okay, so I will. So, okay, hang on, sorry about this. I'll just get this going. So share screen again, right. Is that right now?
Yeah, that's fine. That's good.
And I'm just going to put it full screen, and is that right?
Yep, that's all good.
Great, okay. So one of the things I've put it right at the beginning because I quite often would actually see it not mentioned in a school test or in an exam, and that don't forget the effects of gravity. And when you're talking about extreme Earth events, anything that falls, such as ash from a volcano, sediment in an underwater avalanche, subducting tectonic plate, land after an earthquake shape. It does so because of gravity. So always remember to mention gravity if anything is falling, dropping, or anything like that. So that's just a key thing at the beginning. Now, the first part of this is actually to go through some general tectonic stuff that hopefully you will know, but it's a little bit tricky to try and remember some of it at times, so I'm going to go over it. But first of all, I'm going to talk about the Earth system. The Earth system is a combination of atmosphere, which is obviously air, biosphere, which is land, biosphere, which is life, geosphere, which is land, and hydrosphere, which is water. And these are very, very intertwined, and something that happens in one of these systems is going to affect other systems. And so every now and again throughout these slides, there will be a couple of examples of where you can actually get combinations of things happening within the Earth system. And if I go on to the next slide, particularly at the bottom, for example, heavy rainfall, which of course is atmosphere and hydrosphere, can cause landslides, which is geosphere. If trees, biosphere, have been cut down, so roots can't hold the land anymore, the slip will be more serious. So that's an example how the four spheres have worked together to cause an extreme Earth event, such as a landslide. This is in the standard. It's not been very often asked as a question, but I'm putting that in there just in case there is an examiner that will be asking that sort of question. Okay, so the Earth's layers, I'm sure you know all that, and you know that it gets hotter as you go towards the centre. Remember about the convection currents that actually happen in the mantle, and these are what are spreading the sea floor to create the plates, like the Pacific plate, which is the one that subducts under New Zealand in the North Island, and of course causes mountain building in the South Island. So just a general knowledge about convection currents is important. Right, and you're probably very familiar with this sort of jigsaw of a map showing the different tectonic plates, and you can see that over on the left we're affected by the Pacific plate and the Australian plate. And you don't need to learn that. It's just for a background if some of you are a little bit rusty or haven't done as much work as would like to on this, to remind you about the importance of tectonic plates. And also what's really important is there are two types of crust. So you saw that cross-section of the Earth. The top layer was the crust, and there are two types. Oceanic crust, young, dense basalt rock, very thin, mostly under the sea. You occasionally get a little bit on land, which is usually old oceanic crust, but the rest is under the sea. Continental crust, that's your land, less dense and buoyant granites. Thicker than average, it's usually about 40 kilometres, a bit more if you're talking about the Himalayas, a bit less in somewhere like the Taupo volcanic plateau, where it's actually being stretched, which is partly why our volcanoes are so violent there. Right, and this is actually quite an important map, and I'm not going to spend too long talking to it, but it actually shows the surrounding area according to depth, whereas if you look at that purple strip up the top there, the Kermadec Trench, that actually takes three New Zealands, three Mount Cooks, still getting going. 3 Mount Cooks on top of each other, it is so deep. The darker blue is less deep, but still pretty deep, so about 4 to 6 kilometres. The pale blue is getting not quite so deep again, and then you're getting to the green, which is more a transition zone. And the sort of orange and the red are what is known as continental crust, and the red in particular is the continental shelf around New Zealand, which is immensely important when you're talking about earthquakes can occur on that, and also because they're out to sea can be one of the causes of tsunamis as well. Okay, And here, of course, is the tectonic plate boundary. That is actually going down through New Zealand. Now, if you are drawing a diagram, and if for some reason you're wanting to draw the tectonic plate boundary, notice how it goes down the east coast, the East Cape, Gisborne, Napier, Wellington part of the coast, but notice that it doesn't cut through the bottom of the North Island. It enters onto the land at round about Kaikoura. And I've seen a lot of tectonic plate boundaries rather quickly and lazily drawn that go through the North Island, and that's not right. So make sure that it cuts across from Kaikoura over to roundabout Westport, goes down the west coast and comes out at Milford Sound and then keeps on going down. And so you've got the Kermadec Trench at the north of and the Pusica Trench at the bottom. Right. And here's the different plate boundary interactions. Pacific plate is subducting under the Australian plate in the North Island. And notice the arrows and notice the little kind of triangle-y bits on that. But down in the bottom of the South Island, the Australian plate is subducting under the Pacific plate. Really important that you know that there are two subductions. And I'll show you a better map of that in a minute. In the middle of the North Island, in the middle of the South Island, you've got the Alpine Fault, which is actually moving mostly sideways or laterally. There is a little bit of vertical movement whenever there's an earthquake, but it's mostly lateral. Right, and so very diagrammatic little diagrams showing oceanic crust. If oceanic crust meets continental, it will subduct underneath, which is what we get off the east coast of the North Island. Also to the north of the North Island, we actually get denser, older oceanic crust diving under oceanic crust, and I'll show you a bit more of that in a minute. Something that North Islanders in particular tend to forget is the fact in the South Island you have continental crust meeting continental crust. And what happens then, in this case, the Pacific plate actually goes over the Australian plate and forms the Southern Alps. So the Southern Alps are all actually on the Pacific plate. It's the west coast that is actually on the Australian plate. Now, the Nelson area that I'm on is on the Australian plate, but if I drive to Blenheim, I go over the tectonic plate boundary just before I get to Blenheim or the vineyards. Right. Okay, and these can sometimes be called slipping plates or lateral plates. And this happens particularly along the Alpine Fault. Right, and this is actually quite a good diagram. This is sort of a proper way of showing it. You can see that the little triangles along the line show the direction of subduction. Notice how it's going, the subduction of the Pacific under the Australian is going pretty well kind of at New Zealand up in the north, but it's going down more like that as you get down towards the South Island, which is translating into the lateral movement along the Alpine Fault. And on the down in the south near Fiordland, there you've got the Australian plate coming under the Pacific plate. So New Zealand is kind of being twisted in the middle, which makes for a lot of major fault lines, which I'll show you later on in this presentation. Those diagrams are good though too. So if you're actually keen on drawing diagrams, those are two good diagrams to try and learn. The two subduction ones, the one up the top, A to A dash, and down the bottom, B to B dash. Now, this is actually showing where the different crust is around New Zealand, oceanic and continental, and what is going on there. So starting up on the north, you have oceanic crust under oceanic crust. That seems a bit weird, but the Pacific plate oceanic crust has travelled all the way across the Pacific Ocean, and it's much denser and much older. So the than the Australian plate, which is you can see is the kind of green sort of colour, and that is still all underwater except for Raoul Island and I think Macquarie Island, but that is much higher, so you actually get subduction. And as oceanic crust goes under oceanic crust, it subducts and it draws down the oceanic crust subducting, pulls down the other oceanic crust, and that's how you get the deep trenches. Pusica Trench down the bottom is not quite so deep because you've still got a lot of sideways lateral movement. So you get down to going down the east coast, still subduction Pacific under the Australian plate, round about Kaikoura, where subduction changes to lateral and collision movement. Further down, collision movement, PP and AP producing the Southern Alps. And then on the other side, you've got the Auckland volcanic field hotspot, subduction of AP under PP, oceanic under continental crust and fjordland, and then oceanic under oceanic again when you're down near the Pusica Trench. The Auckland volcanic field seems like a bit of an anomaly. Part of the reason is that the Auckland, the magma is able to come from very deep, and I do go over it better later, come from very deep because that part of the North Island where the Taupo volcanic plain is and sort of going up towards Auckland, that is actually being stretched. And you can see why, if you're interested, you probably wouldn't have to put this into exam, is that those two lines just above the Bay of Plenty, two lines of kind of volcanoes and kind of mountains going up to the northeast, that used to be just one line of volcanoes in that. And over the years, that bit of the crust is actually being stretched as it gets pulled downwards. So it's worth knowing that that crust is being stretched. Only mention why if you're going for excellence. Right, and key places to know. Make sure you know your key places around New Zealand, and they're on here. These days you tend to get a map if an unusual town like Eketahuna was mentioned one year, you now actually get a map showing that where it is, which is useful. But you still need to know these key names. Now we're going to start on volcanoes. There's an awful lot on volcanoes, and just be aware that New Zealand has got a lot of different types of volcanoes. The main ones you're going to be learning about are the Auckland ones, which I'll be doing second, which are the hotspot volcanoes. We start off with a bit of general stuff about volcanoes and then go into the different types of volcanoes. But just be aware there's a lot of different types of volcanoes in New Zealand. So there's an active volcanoes like Ruapehu, Ngārahoe, which reasonably regularly erupt. A dormant volcano is Mount Taranaki. It's not erupting at the moment. It's possibly, potentially due for an eruption, but it's still got a magma chamber with some magma in it underneath it. So an active volcano obviously has got a magma chamber. Mount Taranaki has got a magma chamber. Now, this is different from the Auckland volcanic field, so don't apply any of your Auckland volcanic field stuff to this. These particular ones are subduction volcanoes. And then you get an extinct volcano, e.g. Banks Peninsula, and you can actually see collapsed craters there, but there is no magma chamber under it, or it's completely empty. And so there is no... that's an extinct volcano, no chance of it erupting. A lot of people were worried about when there was the Christchurch earthquakes that was going to make the Banks Peninsula earthquakes come alive, but it couldn't. And scientists had a lot of trouble at times saying, no, there is an empty magma chamber, it's not going to happen. And these are products and results of a volcanic eruption. Notice that magma is the liquid rock underground, lava is the hot liquid ground. Rock on top of the ground. Volcanoes just don't only erupt lava, they also erupt ash as well. ash can be very fine and goes up into the air and then becomes a cloud, which is sent a certain way because of whichever way the wind is blowing, and that's the cloud that stops airplanes from flying. And then you can get the cloud will also collapse and form a pyroclastic flow. If it gets mixed with a whole lot of water and stuff, then it can become a lahar. And I'm not going to go over that because that just says a bit more. But the standard states that you need to know about the effects of earthquakes as well. So these are just general effects, either whether they're hotspot lava flows or whether they're subduction, it doesn't matter. And so this was actually taken in Hawaii, where you can get very runny lava flows. The lava is very similar, very runny, low in silica in what you would actually find in the Auckland volcanic field. And people often know this lava flow is coming, and they will evacuate their houses at the last minute. And when they buy land and build houses there, they know that they could get lava through their house. And so I'm sure they've got enough sense to make sure that everything is movable. The next one down below, you can see the volcanic ash being kind of sent along in the wind there, and you can see some of it actually also starting to fall down because of gravity as well, and that's Ruapehu erupting. On the left-hand side, that's a pyroclastic flow. Now, pyroclastic flows can be utterly massive if you've got something like Taupo erupting, but also be aware that Narahoe, a small mountain, will erupt with a pyroclastic flow, and also certain types of Auckland volcanoes will erupt with a pyroclastic flow. They're not quite, from a smaller volcano, they're not quite so dangerous, but from big volcanoes, they're terrible. And that's actually, we've got our own Pompeii that is actually near Tararewa, and that was a village buried by ash and pyroclastic flows from Tararewa eruptions. You can get volcanoes collapse. There's White Island showing one side collapse, and there was a very famous disaster, which I'm old enough to be able to remember, called the Tangiwai disaster, and that was because a full crater lake in the top of Ruapehu actually overflowed and sent a lahar down the side of the mountain and took out a bridge just as a train was coming at Christmas. And I did leave those pictures in; they were pretty tragic. And also the next one there is now is early warning measures put in place. And not too long ago, in 2007, the crater looked like it was going to overflow again, and the warning places worked. And you can see the two photos on the right-hand side, and that shows one before the lahar flow and one after the lahar flow. So they were able to close the roads. They'd rebuilt the bridge really strongly. They'd closed the roads. They stopped people travelling. The lahar passed harmlessly under the bridge. Didn't cause any damage. Effects of volcanic eruption can also be gas, and you don't want to actually breathe in too much volcanic gas, because that can actually poison you. And people have died in enclosed hot water baths in Ruapehu and Rotorua and places like that. Okay, magma. Now, what's really one of the really essential, important things that you need to learn for any volcano question is the relationship between magma and the amount of silica in the magma and how that affects viscosity or stickiness. And the amount of stickiness is also related to the amount of gas it can trap, which also relates to the violence of the eruption and also the shape of the eruption. And you very much need, and I'll come to the table in a minute, you very much need to make sure that you're absolutely on top of that and that you have learned that. So notice that the temperature varies. So here's the table. And basaltic I've actually got, that actually relates mostly to Auckland volcanic eruptions. And you'll notice there, I'm not going to go over each one in detail because you can actually look at that. You will very occasionally get basalt reactions in the Taupo volcanic zone, and that's because the crust happens to have stretched enough to kind of let some of that magma through. But generally, the andesitic and the rhyolitic are the types of lava, type of eruptions that you actually get in the type of lava that you get in the Taupo volcanic zone. So absolutely essential, you know the relationship between type of magma, amount of silica, viscosity, temperature, amount of gas, and the eruption shape that you get. I'll be going over that a bit more. Right, types of erosions. There's Narahori erupting, and it's really good because you can actually see the ash cloud going up into the air, but you can see how part of it has collapsed, the heavier part, and that's a pyroclastic flow. And there was actually a teacher I actually watched that eruption, and there was a teacher that I was teaching with later on who said that she was actually running down the mountain away from that pyroclastic flow, and luckily she did get away. But that's what a pyroclastic flow would look like from something like Narahori erupting in a normal way. You can also get hot magma coming up under a water source such as a lake or ocean. Now, this can happen with subduction volcanoes, and so, for example, Tongaway, you can get suddenly volcanoes coming out of the sea. Those are still subduction volcanoes. You can also get this type of eruption as a very common Auckland eruption as well. So just letting you know about that. Okay, this is still effects of it. The types of tephra, you hear about tephra. And so, for example, that's scoria on the left, cinders, that you get that from your Auckland volcanoes. Fine ash, that looks like it on the right, it looks like it's come from rhyolite eruption, and a big volcanic bomb. And I watched them coming out of the Narahori, and some of them were the size of houses. They're enormous. Okay, volcanoes are formed in New Zealand in two ways, subduction volcanoes and hotspots. Make sure you definitely know the difference between them. It is essential. It's essential that you read your question carefully, and particularly if it's volcanoes, you identify the type of volcano. It may actually state it in the question, or it may give you a big hint in the question. It'll be one or the other. You will be able to identify it, but make sure you do. And I've seen answers where they've talked about hotspot ones when it's actually a subduction volcano and vice versa. So make sure you identify the type of volcano. Okay, now this is a little bit repeat of what we just had before, so I'm not going to go over it, and you've seen that before. And this is the two types of crust again, but a point that I wasn't made before is that tectonic plates can have oceanic crust and be made up of oceanic crust and continental crust. And you saw that in one of the maps further back where you saw the Pacific plate, for example, is oceanic off the North Island, but it's oceanic and continental when it's down by the South Island. And the same with the Australian plate on the other side. All of the North Island is on the Australian plate, but also the Tasman Sea is also on the Australian plate as well. And oceanic crust is under that. And there we've got it. Okay. So this is the importance of oceanic crust and continental crust. It's pretty much what I've gone over before. It's also identifying key volcanoes, and so that you may either get one of these volcanoes or something pretty much like it. And so that's why I've kept some of these examples in. Okay, formation of subduction volcanoes. It's when the oceanic crust dives under the Australian plate, under the North Island and along the Kermadec Trench. Make sure you realise it's oceanic under oceanic, the Kermadec Trench, North Island, oceanic under continental crust. Now, as the Pacific plate subducts, it gets warmer at a certain depth, it gets hot enough for magma to form. And rising magma, this is just a very brief summary of it. The next page slide, I go into a lot more detail. Rising magma forces its way up through cracks in the crust, forming subduction volcanoes. However, it's and this, notice that this only happens at a certain depth. Now, so the first one on the right, that's the Taupo volcanic volcanoes. The one on the left is Mount Taranaki, which is a little bit of an aberration, but it still is a subduction volcano. But the Taupo one, of course, is all the the Calderas, Taupo and Rotorua and Tarabia and others like that, and then also the cone volcanoes of Ruapehu, Tongariro and Ngātahoe. And because the magma only starts at a certain depth, which is why you actually get lines of volcanoes. And so going right down from some sort of next to the Kermadec Trench all the way down as far as Ruapehu, you have got volcanoes in a line because that's the depth the Pacific plate has dived down, and that's where the magma is formed. Okay, now wet sediment from the ocean floor also plays an important part, and the next slide is an important one as well. So I'm going to go over that bullet point by bullet point. Pacific plate subducts under the Australian plate assisted by gravity. So there's your gravity as well. Water-laden sediments are subducted. The Pacific plate gets warmer the more deeply it's subducted because it's going nearer the centre of the Earth. It's going to about 20 kilometres in this area. And remember 20 kilometres because the magma from hotspot comes from way deeper. When it's subducted to a certain depth, the water becomes superheated and it lowers the melting point of the rock of the overriding Australian plate, melting it. Right? So this superheated water is one of the primary ways that magma is made. The melted rock forms magma, which, because it is hotter, is less dense, so it rises towards the surface through cracks in the crust. Now, you can find out a little bit more about, if you've got this book, you've probably seen my name from the bottom, and I actually wrote these chapters, and so this is a good book to learn from if you're able to get hold of it. Otherwise, these PowerPoints are all online for you. Okay, going on. This is also how gas makes volcanic eruptions explosive. So this is also important. And basically, as the magma is forming, other rocks like limestone is melting. And limestone, which you probably remember from your year 11 chemistry, is calcium carbonate. And if that gets heated, it releases carbon dioxide. These gases get trapped. The more viscous, the stickier the magma, the more gas gets trapped. As the magma rises, the pressure's going off, so the bubbles get bigger and bigger and bigger. And if you've made hokey pokey, it's just like making hokey pokey. As this rises, the gas bubbles get bigger and bigger and bigger until you get a massively explosive eruption. Eruption in the really violent rhyolitic volcanoes, and a not quite an explosive but not quite as explosive eruption in the other types of subduction volcanoes. So that's also important, and this is a little animation which doesn't seem to be working at the moment, and I'm just going to flick on because that is just, oh, there we are. It's just expanding it. Okay, there's the Taupo volcanic zone. You should be familiar with that, and I'm not going to go over it. This is a good diagram to learn if you want to learn diagrams if you're good at diagrams in the exam. Remember what I mentioned about the crust thinning. Also, magma actually gets ponded up underneath. You can actually see this in a crust, and that also helps make the volcanoes quite violent. And there it actually shows Taranaki. Okay, 3 main types of volcanoes in the Taupo volcanic zone: subduction volcanoes, cones or stratovolcanoes. Notice those 2 different names. Sometimes an examiner will use a cone volcano, sometimes we'll say stratovolcano or something similar. Again, make sure you know what type of volcano you're talking about. Those mostly andesite lava, calderas, rhyolitic lava. And domes are quite cool. They literally are, sticky magma which arises up of the ground, usually near where there has been a very violent gaseous eruption, say even just a few thousand years ago, and so there's no more gas. So you get like sort of squeezing a test tube coming up. And Mount Tarawera has got that, and also Mount Maunganui is actually a dome volcano. And all over that part of the country, you can see small dome volcanoes. Okay, so I'm not going to go over this cone volcanoes, andesitic lava. It's kind of in the middle. They're explosive, but not too explosive. They alternate between, sometimes it's ash eruptions, sometimes it's lava eruptions. And there's some examples. Here you can see Ruapehu, Naraho, and Tongariro, and I'm going to keep going. This is good stuff for you to look over and good photos. And because I need to do hotspots and then I need to get onto the other stuff as well. Now this is calderas, and they are very violent, and there's a whole sequence of why they're violent, and there's good diagrams, and they also are good diagrams that are worth learning to answer questions. Okay, there's a dome volcano, there's Mount Maunganui there, Mount Tarawera. Also showing the Kermadec volcanoes. I think there was actually a question on Kermadec volcanoes one year, so I'm making sure that you know about that. This is all happening under the sea, remember, except for Raoul Island, where there was someone died in a volcanic eruption just a few years ago. And you get the same thing. You get high volcanoes, you get calderas, collapsed cones, all that sort of thing as well. Okay, geothermal systems, again, I'm not going to go over them, but it is water that is trickled down towards a magma source. It gets heated, and then because it's hot, it sort of squeezes its way up. And also notice that steam eruptions can also occur, as happened on White Island or Kari Island. They don't give you any warning. It's not magma moving, so you don't get earthquakes, and which is what gives you the warning of eruptions often. So steam eruptions they're dangerous because of that. Okay, Auckland volcanic field. I'm going to go through this fairly quickly. Make sure you have your sense of scale right. Notice that the red line isn't very prominent, but the red line that shows the width of Mount Eden, if you take that red line, it only just fits into Crater Lake. So Mount Eden, basically, not the huge lava flows, but the little cone of Mount Eden fits into the Crater Lake. Notice that if you go across the width of Ruapehu, that fits into all of the CBD of Auckland and beyond. So make sure you've got that sense of scale, particularly if you're in the bottom of the North Island or the South Island, you haven't travelled much to Auckland, you're looking at much smaller volcanoes. And they don't all have their own magma. The magma comes from a hot spot about 100 kilometres. Remember, it was only 20 for subduction volcanoes, 100 here. This is very hot, runny basalt, low silica, no water. There's no water trapped in it, so you don't get spectacular eruptions like the Taupo volcanic zone eruptions. That you can read through that. There are two different types of eruptions, one of them that have come up from underwater, and that long word in yellow is phreatomagmatic. You don't have to learn that. And they are often what form your nice little lakes. And on the right-hand side, you can see a little lake in Mangere, which would have been formed from that phreatomagmatic eruptions, and then also a cone, which is formed from when you get very hot magma coming up under land. And so your cones, Mount Edens, One Tree Hill, Mount Wellington, they have actually come from these type of eruptions. And you do get a bit of a sort of fire fountaining, so they'd be quite pretty to watch. And then, of course, Auckland has got a lot of sort of huge lava flows of this runny basalt. And runny basalt is very hot, 100 degrees centigrade, runs for a long period of time before cooling. And so that's partly why you get your cone shape of Rangitoto. and I'm not going to spend too much time on this. Now, earthquakes. I've got earthquakes and tsunamis, and I'll be pretty well going. I'll stop at 5-2 and see if there's any questions. Earthquakes, notice that they can be caused by volcanic activity coming up under a volcano, and it's stretching the crust as it comes. So you can get clusters of volcanoes, and seismologists and volcanologists know how to read these. The other thing is tectonic plate movement, which of course is the big reason for earthquakes in New Zealand. And you know about the boundary, we've done that before. There's those diagrams again. Notice that faults can be offshore or on land. And so there probably is faults as yet unmapped, a lot of them, and there's a lot of the continental shelf all the way around New Zealand. There's only some of them in that right-hand diagram. There's also these systems of great faults, and you can see that in the map on the left-hand side. And that you can see them from the air. And left-hand side, you can see the Marlborough faults, several in a row, and going up into the sort of into the North Island as well. The Alpine Fault, and Alpine Fault is very, very definite on the map on the right, on the photos on the right. Okay, now one thing, this is a really important page here because people can get fused between tectonic plates, and then it's called the Alpine Fault, but it's still the tectonic plate boundary. And then, of course, when we had Christchurch, we realised that fault lines didn't need to be anywhere near a fault line or the tectonic plate boundary or a major fault line. So the thing to remember is the Pacific plates and the Australian plates are moving, converging, sliding past each other.
We have a quick question.
Yeah,
that's right. Someone asked, just going back a bit on subduction, I was taught that the friction between the AP and the PP cause basaltic matter from the PP to melt, and due to its density, it slides down, then superheats, then rises.
That's kind of like the very simple, a lot of the stuff you learn complexity as you go on through, say, learning earth sciences. The very simple explanation of friction is only a very simple and only very minor part of it. With subduction volcanoes, the major part is that superheated water breaking up the rock. And that's been in all the notes and in the textbooks for a long time now. Yeah. Okay, right, shall I keep going?
Yeah, keep going.
Okay, good question. I'm really glad you asked it because I think, that is still in old textbooks, but it's certainly not in anything that I've written. Okay, if the person wants to form feedback to their teachers and they get the teachers to email me, you can... it's very easy to find my email, and I'll make sure they've got the resources with the right stuff on it. Okay, so what's actually happening is tectonic plates are moving all the time, and as they're moving, they're subjected to stress. So they're slowly distorting as they move along, and stress builds up. Stress is released by huge cracks in the crust. Those are fault lines. They might go directly along the tectonic plate, but they might also be well away, like the Christchurch ones, from the tectonic plate. And then so the fault cracks initially, and then it might sit there for tens, thousands, even millions of years, just building up. And the tectonic plate is still moving and still stretching and still distorting, and tension is still building up, and the fault is kind of sticking together either side of it, gaining elastic potential energy from the moving plate, and then all of a sudden one day it'll move very suddenly. And that is what happened in Christchurch. That Greendale fault was a fault that had been there before. No one knew it was there, but it was there, and then it hadn't moved probably for about 14,000 years, and all of a sudden one day it moved. So really important that you learn this page and you understand that, okay? Faults can be as short as a few metres or as long as 1,000 kilometres, and the Alpine Fault is certainly about 500 kilometres long. And there we are. I've talked about the elastic potential energy. builds up, and then it actually gets released, and it gets released as seismic waves, which of course will be kinetic energy plus vibrational energy. The focus is where the fault first breaks underground. The epicenter is where the seismic waves first reach the surface. Right, and this is, you can read this. I've got examples of different earthquakes here. Darfield earthquake, and here's an important point: the shallower the earthquake, the stronger the shaking, and the more dangerous they are to people and buildings and that on the ground. And Christchurch showed us that you could get an enormous amount of aftershocks, but the Kaikoura earthquakes, paradoxically, showed us that you didn't have to have a lot of aftershocks, and that is why they were able to get the roads so quickly fixed in Kaikoura and get State Highway opened up quickly again, was because they didn't have nearly as many aftershocks as Christchurch did. So, just shows that earthquakes are different all the time. You can also get, now those earthquakes, Christchurch earthquakes, is because kind of plates that is when you've got plates sort of colliding together. But you can get, where the land is stretching, you can get what's known as a normal fault, and you'll see the diagram to the right. And there the land slumps down, and that actually creates land. The other ones I'll show you in a minute. A strike slip fault, you've just got sideways movement, and that's a picture from Christchurch. And then that shows a reverse fault, when actually, in actual fact, you lose a bit of land. And you'll have time to read over those, hopefully. That is actually a exposed fault line in Nelson, very near where I live, and it actually just shows that there is micro movement going on between the sides of a fault line rubbing all together. That's what's created that dark band, which is about 2 meters wide. And you can also see the rock. The rock to the right is crumbly and to the left is crumbly, but you can only pull big chunks of it. That darker rock, you can literally go like that, and it crumbles in your hands. And here you can actually follow, these are small faults, but you can follow a line of darker strata along, and you can actually see the movement along the fault lines. You can also get them happening when one plate subducts under another, and land above it can crack, and you can get earthquakes like that. And the Napier earthquake was one of those. Also, sometimes you get a subducting plate abruptly thrusts further down, and this happened in Fiordland, where you got actually, I think it was a 7.8 earthquake there. And this is just showing deep earthquakes. As the earthquakes get deeper, that's actually proving the subducting plate is going deeper. Notice where the Alpine Fault is, there's no deep earthquakes because it's mostly sideways movement. But as soon as you look at shallow earthquakes, you can actually see that there's masses of earthquakes there too. Different seismic waves. I'm sure you've learnt about P and S waves. P arrives first, and if you can actually hear an earthquake coming, it's the P waves that have left the ground and vibrating the air. S waves are both surface waves. The other waves they're the ones that go through the earth. Secondary wave and the Rayleigh waves are the ones that go up the surface, and in a big earthquake often do the most damage. And there's a moving diagram there. Seismographs, I'll leave you to read that because I'm aware of time. Earthquake scales, there's two. One, the Richter scale, which is the magnitude of an earthquake, the amount of energy an earthquake releases. But if you want to actually describe kind of what's happened on the ground, you use the modified Mercalli scale. So slightly different scales. And there's the Mercalli scale there. Now, I'm just going to flick through this, but this is showing major fault lines. And this is also showing, there's the Wellington faults, a little bit about the fact the plate is stuck under Wellington. And then some historical ones to just give you an idea of the effect, what actually happens with Murchison earthquake. That's Nelson College, which is right down the road from me. Murchison earthquake, which isn't too far away. Right. Ngangahura, Ngangahura earthquake had terrible slips. That was the Edgecombe earthquake, Christchurch one. And in the Christchurch one is all the information about liquefaction, which you can learn from there. And that shows the two major earthquakes in Christchurch. One, of course, which was so destructive of life and property. And there's more liquefaction pictures. Certain earthquakes. And the Kaikoura earthquake, which was a very complex earthquake with lots of faults moving. And the Alpine Fault one, where I live, we're all kind of waiting for it to happen, which will happen sometime. Megathrust earthquakes, don't read through, just read quickly, flick through that so that you know that they exist. The megathrust earthquakes are when you get the one plate pushing its way under, and they can cause quite large tsunamis. Now, I've just got a little bit of time to go over tsunamis, so I will take 5 minutes on this, and then we'll have time for some other questions. There's a little bit of the history. New Zealand has got a history of tsunamis. You can find the history both geologically and orally in the Whakapapa of Maori, and that talks about that. Now, what are tsunamis? Giant waves that displace water, and they displace the whole water column, and the water column is right. You know, if an underground, if a bottom of the sea earthquake has happened 4 kilometres down, it is a whole 4 kilometres of water that gets displaced. And so, a tsunami can be caused by anything that displaces water. So even a small stream could have a landslide go into it, which, causes water to be displaced downstream. It also might dam water, at which then erodes through the rubble and eventually causes a flood too. So those are the effects. But the important first thing is that something happens to displace water. And the largest tsunamis are the ones where you get underwater or massive seafloor earthquakes, or you can actually get sediment accumulating on the side of underwater canyons, which I'll show you in a minute. And with a very strong land earthquake, the shaking may be enough to just cause the sediment to slump, again displacing water and causing tsunamis. There's a bit about the speed of tsunami waves across ocean when they're in the ocean. So if they're coming from across Chile, because New Zealand can get tsunami waves coming across from massive earthquakes in Chile, then they travel very fast. And if you're out in the ocean in a boat, you wouldn't know that a tsunami was happening, because they have a very, very, very long wavelength, but aren't actually very high. As they get closer to the coast, the wavelength gets shorter, and the amplitude, the height, gets much higher. And so there's an example there. And notice that wind waves only occur on the top of the ocean. They come and go without flooding massive amounts of higher ground. You may get a storm surge, but that's all. Tsunamis, particularly if it's been generated by a huge underwater earthquake, you can get tsunamis coming on and on and on and on into the land, and flooding masses of stuff that wind waves or a storm surge wouldn't do. And so there's also showing that there. Often when we're talking about tsunamis, we think about larger ones that are generated by underwater earthquakes, but they're not necessarily. So remember that. And this shows you your wavelength getting shorter and your wave height getting higher and more of a run-up. And of course, luckily these days there's now a lot of warnings about tsunami, but basically if you're anywhere at the coast and you see the sea growing out on that a long way, or you get a long earthquake or a strong earthquake, then get the heck out of there as quickly as possible. If I take my grandchildren to the beach now, I always notice where the car is and we don't go too far from the car. Okay, these are the tsunamis that come from overseas, and they can still actually have quite a massive run-up. This is just to remind you that there's a lot of underwater faults as well that may move and can cause tsunamis. And then this goes through how tsunamis are generated. I'm only going to go through this quickly. Now, you must have either, if it's an underwater earthquake, the land either has to go up or go down. If it goes like that, then there's no earthquake because there's no tsunami because there's no displacement of water. You've got to have that displacement of water. If it goes like that, it's going to displace. If it goes like that, the water's got to drop and then it rebounds. Okay, so this explains that, and you can read through that. Now, notice all the things. There's a lot of volcanic eruption things that can happen. Undersea eruption, pyroclastic flows, lahars, underwater avalanches, ice falling off the end of glaciers into lakes, which is called cavas, for those of you who live down in the South Island. That shows a landslide and it shows a pyroclastic flow. If that went into a lake or a bay or something, it could cause Bakari White Island has already collapsed once, and it shows a diagram there of what potentially could happen. Underwater Kermadec volcanoes, they often collapse and leave masses of pumice floating around the top of the sea. Diagram showing that. You can get landslides going into sounds like the fjords down in Fiordland. That generates a tsunami. You've got the continental shelf going right around New Zealand. You get major canyons like the Cook Strait canyons, and the sides of them can collapse, or the sediment can collapse off the sides to produce tsunamis. The sediment gets sort of swept up from the erosion and weathering of mountains, gets swept up and gets put onto the side of volcanoes, and then it collapses down. So if this Kaikoura Canyon is a kilometre deep, the sediment is a kilometre high. If that falls down, you've got a whole lot of gravitational potential energy translated into a massive amount of kinetic energy. Historic tsunamis, there's just a few here that I've got. And then that's the end of that. And we've got 3 minutes, I think. Are there any questions, Andrew? Shall I stop sharing?
We had one question. What are the energy changes / transfers in a tsunami caused by an uplift?
The same thing. If you displace water, you're going to you're obviously going to give that water energy, which is going to form a wave, and the wave will be moving, so that's kinetic energy. So if it goes upwards, it's not actually gravitational potential energy in that way. It's certainly elastic potential energy has been released, because there would have been a massive stress on that fault line for it to be suddenly released in a massive earthquake. And I think the Boxing Day tsunami a while ago now, 2004, I think, was that was something like a 9.5 earthquake. So there must have been an enormous amount of elastic potential energy stored, which got released and then translated into kinetic energy and wave energy. Okay.
Well, I think that's all the questions. So we'll have a 5-minute break and then come back. Just go to the end of the PowerPoint, Jenny, and just leave it there. So it'll be a blank screen. And then we'll be back in 5 minutes and just mute.
And I'll stop sharing too.
Yep.
Yeah, because it'll be another PowerPoint next year.
Oh, okay, yeah. Stop sharing and then just mute your camera and mic.
Okay.
We'll be back in 5 minutes.
Okay. Hi, Andrew. I'm ready when you are.
Yep, we'll make a start. We said we'll start at 11:05, but there's still 11 people on here, so we'll share your screen and make a start.
Okay. Are they the same 11 as before or new ones? Because often only people are only sitting one, sometimes only sitting one standard. So
no idea. Normally it changes. I can just say there's 11 people on. That's it.
Okay. Well, I might do this very quick introduction as I did before. They don't necessarily need to see me, but I'll just mention about making sure they do diagrams and that sort of thing. Okay, so we're starting?
Yep, we're already streaming.
All right. Hi, everyone. It's Jenny back again, and I'm not too sure how many of you have joined just for the stars and planetary systems section, and so I just want to mention again that when you are doing this exam, you'll have 3 questions. One is often kind of roundabout on the HR diagram. Another is usually on the birth and death of a star. And the third one is on a planetary system, or maybe the formation of moons, formation of a planetary system or the formation of moons. So, and it's often the latter one that is actually done quite badly. So we'll try and make sure we've got a bit of time on that. Remember that there is room to draw a diagram, and that if you are very good at drawing diagrams, and as long as you label them and annotate them really well, then they can actually certainly go towards you hopefully getting a good grade. I think those are the key things. So I'm now going to share the screen and get on with this, and best of luck for when the exam happens, which I think is tomorrow. Sorry, I'm just going to have to open up this close down the old one and open up the new one. So, oh dear. Andrew, you still there?
Yep.
Oh, good, because that's right. I can okay, so here we go. Right, can you see that?
Just give it a second. It should. No, nothing's come through yet.
Well, I'm not too sure whether I signed myself out by accident.
No, you're still on. You just need to click on the Skype button and then hit share screen.
Oh, maybe, yes, that's the same. Oh, now I've got you all back again. Yeah. Okay. Sorry, this is taking a bit of time. Right. Yep. Now we're right. Can you see it now?
Yep. Very good.
Excellent. Okay, so we're back again now. And so again, this is another one of those PowerPoints that will actually be put into, will be called Revision Stars and Planetary Systems, and that will be put into the relevant folders that are being shared at the moment. So I'll do that as soon as we finish this in a bit less than an hour's time now. Okay, so because it's at the beginning, really, I'm going to go over the stars stuff first, and there's some general stuff at the beginning that's kind of background that you need to know, and then we'll go from there. So there's a bit about what exactly is a star, and the fact that they are born, live, and then die. And the mass of the star, when we're studying stars, the mass of the star is very important. And in astronomy, because numbers can be so big, with astronomy, how we do it, we often use, we simplify things a lot. So, for example, the sun is one solar mass, and all the masses of other stars relate to the mass of the sun. So that kind of makes it easy for us to understand. A similar thing is the distance between the sun and planet Earth, which is called 1 astronomical unit, which I think is 150 million kilometres. And although sometimes the Earth is a bit closer to the Sun and a bit further away, on average it's kind of 150 kilometres, 1 astronomical unit. And then all the other planets are less of an astronomical unit if it's Mercury or Venus, or more than 1 astronomical unit. But again, that distance is called 1 astronomical unit, and it means that we're able to get a good sense of the scale of things without having such big numbers that our brains get too stodged up. Okay, we only actually see the brightest stars, and they're different colours. And there's the structure of the star, and what's important for us is that you realise that there's a hot, dense core, and that's where the main business happens, the nuclear fusion, which in the general main sort of star is hydrogen fusing to helium. And the outer bit is a gas shell, which helps move heat from the core to the surface. And stars have a balance between gravity pulling atoms into the centre and the pressure of the heat and light radiating out. Okay, and measuring distance within the solar system, you use astronomical units. Beyond the solar system, you actually use light years. And light travels incredibly fast, at 300,000 kilometres per second. And so a light year is obviously going to be the most phenomenal amount of large number. So it's very easy just to say light years, talk about light years. There are other ways of measuring even further out distance, but we don't worry about them. Okay, also different energies, luminosity, the amount of energy a star radiates per second. And again, here you have another, and I think it's standard measure. I'm not too sure they've got that term right, but it's something that relates to the sun. And 1L, luminosity, is the luminosity of the sun. And so the other stars are compared to the luminosity of the sun. It's important and often gets asked about apparent and absolute magnitude. So apparent magnitude is how bright a star appears to us. Absolute is the actual brightness. And I'll give 2 examples. Sirius, the brightest star we can see, greatest apparent magnitude. Canopus is the second brightest, but its absolute brightness is greater because it's much further away. Good that you know that, and also just remember absolute magnitude, because that comes up when we're talking about the HR diagram. So that's actually how bright the star is, which is different to the amount of energy. It's related to the amount of energy star radiates, but there's not a direct thing. Temperature measurement in astronomy, we measure in something called Kelvin. It's the same size unit as Celsius, which is what we do in everyday stuff, and in earth sciences we're using Celsius, but here it's Kelvin. And you don't need to worry too much about the comparison of Celsius and Kelvin, but it's just interesting. There it is. So absolute zero, which is supposed to be the coldest that you can actually get to, and it's minus 273 degrees centigrade. Of course, it can get phenomenally hot. So the temperature inside a supernova, for example, would be several million degrees Kelvin. Okay, and the colours of stars run from blue at the hottest and red is the coolest. And if you find that a little bit kind of round the wrong way for you, in the days when I was a kid, we often used to put pokers in the fire, and you had to open fires in those days, and the poker would go red and then it would go yellow and then it would go white. We never ever actually got it to blue. You do see that with a dimmer switch in a room or a ray box that you might have at school. If you turn it right down, you actually get a red light. And as you turn it up, give it some more power, which means it gets hotter, then it'll go to yellow and then to white. You don't usually get the blue light, but blue is actually the hottest. And so this is the surface temperature of stars, and colours are related. This also relates So you notice the difference between the hottest stars and the coolest stars, and a bit more of that in a minute. And in the next slide, we relate this to actually spectra. There's different spectral classes. You just kind of have to be aware of that rather than actually do a hardcore learn of this. But I would certainly if you're into merit and certainly into excellence, I would make sure you know the spectral class. There's usually sort of quite funny acronyms you can make with that. Okay. The small, cool K and M stars are the most common. Very hot, large stars are very rare. Now, light spectra and the colour of stars, and you all at some stage would have split up one light, and you know that it goes into the colours of the rainbow. So you get a spectrum, and this spreads the light into different colours to form a spectrum. What happens if you've just got white light, you get that violet through to red spectrum. If you're actually taking a spectrum of starlight, you can get dark lines across the spectrum, and it's actually each element has a unique pattern of absorption lines, and it's like a barcode, exactly like a barcode in a supermarket, except they're obviously a lot more complicated. But you can actually tell, for example, if we actually go to the sun, there is the spectral analysis of the sun, and from that you can work out that those 6 elements are the main ones that make up the sun. And by using the spectra, you can actually find out about the colour, the composition, the age of the star, all sorts of stuff. Okay, and there are 3 types of spectras. The white light I've already told you about. The one down the bottom is starlight, but some of you may have done an experiment in the lab where you actually heat the gas and you sort of get the opposite of the absorption spectrum. And it's quite a cool experiment to do. Okay, and you get a Doppler shift can be shown and that's just extension only. If you're going for excellence, then maybe know about the Doppler shift. If the wavelength gets, I've forgotten exactly how it goes now, but as the wavelength changes, Andrew, can you remember? It goes towards the red light if it's moving away.
If it's moving away from you, the light gets shifted to the red end of the spectrum because it loses energy.
I had it right. Yeah. And yes, no, that's good. That's good. Thank you for that clarification. Okay. Well, it might even be on the slide. Absorption lines move towards the red, vice versa. Stars or galaxies moving towards us. Okay, now the next thing is actually the HR diagram, which is a really important diagram to know about it. And different things, you can actually get different sorts of HR diagrams. They all are actually telling you the same information. But you have to really concentrate when you're actually looking at the HR diagram that you are given, and it's really important that you identify what the axes are showing you, and I'll explain more about that in a minute. The HR diagram can tell you a whole heap of stuff about a star, and you may get asked about any of these. Temperature, colour, luminosity, radius, age, total lifetime, mass, state of life cycle, how the star will die. There's a huge amount. So let's actually look at an HR diagram, and I've got about 3, just so that it's a good idea to look at different HR diagrams so you get your eye in looking for key things. The most dominant thing about an HR diagram is that main sequence that goes right across from the top left to the bottom right corner. And then below that are the white dwarfs, above that are the giants. To the left are the blue giants, to the right are the red giants and the super giants. Now, in this case, you've got something quite simple. You've got temperature along the bottom, and you've got luminosity on the y-axis, temperature on the x-axis. Notice that with luminosity, where 1 is, and remember that 1L is the sun. With temperature, you're going right from on the main sequence. The red ones are the very low temperature, and the high temperature ones tend to are the blue ones, and then you get all that kind of range of colour in between, orange, yellow, white. Not the colours of the rainbow. Don't confuse it with the colours of the rainbow. Okay, so this has just got temperature, and this is just and luminosity. So how much energy the star is giving out. And the position makes sure that you know where the white dwarfs are, where the blue giants are, where the supergiants are, where the main sequence goes. You won't be asked to join this, to actually draw this from scratch, but by golly, you have to be able to interpret it, and you have to know which axes are which. And so here's actually a better one in that it's actually got, notice, temperature on the x-axis, spectral class still on the x-axis, but up the top, luminosity on the y-axis with 1 in the middle there, and then on the other side is absolute magnitude. Now, absolute magnitude is a bit weird. Oh, sorry, I'll flip to the next one. And I've just got to shift. Okay. It's measured unusually. Plus 20 is very dim and low mass. Minus 10 is very bright and high mass. There's no way we need to go and why that happens. And any questions you're likely to be asked will be about luminosity. And if it is asked about absolute magnitude, then just make sure you know your spectral class and your luminosity and your temperature, and that you can then just work it out from the graph. Okay, so the only thing added extra that I've actually added there is where black dwarfs are and where red dwarfs are. And this is actually showing mass here. And because mass also, in fact, the mass of the star relates very much to its colour and things I'll go over in a minute. I've got another slide. So notice how the red dwarfs is 0.1 M sun. So remember that the sun is one mass. And then the ones near the top are actually, it's showing 10 mass, and even over that, the supergiants are up to 30 masses, sun masses. Okay, and here's a much more complicated one. Now, if you're looking at the axes, there's luminosity on the y-axis and temperature and spectral down the bottom there. So that's why it's important to locate your axes, make sure you know where they are, make sure you know what they're about. And this is also actually showing lifetime. So notice that the blue stars have a way shorter lifetime. They're the live fast, die young ones. And then way down the bottom are the more conservative red stars that just putter along, slowly burning up their fuel, and they live for an awful long time. Notice that that the mass, as the mass increases, the lifetime decreases. And that's because increased mass, increased temperature, increased kind of faster use of fuel. Right. That pretty well I've said what is there, so you can read that another time. And this is just a useful thing showing there's far more red stars than other colours, but we don't usually see them unless they're giant. We usually see white, blue and yellow ones. But if you're interested in exoplanets and exostars at all, they're looking for exoplanets around the red ones because they're much dimmer and it's much easier to pick up planets orbiting. Okay, this is more HR diagram, which I have already gone over, but it's here in writing if you want it. Now, what's important is the stars and the fuels they use. This gets repeated a few times through the PowerPoint. And notice now brown dwarfs, which are way down at the bottom sort of right-hand corner of the HR diagram, they never start fusing hydrogen to helium. They're rather sort of sad stars who never sort of quite made it, too big to be a planet, too small to be a star, and that just kind of wander around. Red dwarfs, hydrogen to helium over. They never form a red giant. Sun-sized stars, they fuse hydrogen to helium when they're on the main sequence, and when they become a red giant, they fuse helium to carbon or carbon and oxygen, but they're not big enough to start fusing carbon. We leave that up to the giant stars and the supernova, and they can fuse hydrogen to helium, then they can fuse helium to carbon, And then carbon can be used as a fuel, and a whole lot of other elements get formed until iron is formed, and then at that stage the star becomes supernova. And that gets explained a bit more as well. This explains everything I've just said, this table. Right, main sequence stars are the most common in the sky, and the more massive these stars are, the brighter, the hotter, and they live for a shorter amount of time because they burn the fuel the quickest. When hydrogen runs out, they stop being a main sequence star and they become another type of star. Okay, and this is just telling you about other stars, which we're going to go over in a minute, so I'm going to flip through this one. And there's lots of different dwarf stars. Don't know if you'd ever get a question on that, but red dwarfs are the ones that are proper stars, but just burn hydrogen to helium slowly. White dwarf is like the final stage of our planet, second to last stage, and then black is the last one, and then the brown dwarf is the one that's too small for nuclear fusion. There's also neutron stars and pulsars, which I talk of as well. Now, the birth of stars, the first part is this has got stages, and it always starts with these cold, dark, enormous clouds. Now, they've got two names. I always like using stellar nebula, but they're also called giant molecular clouds. Now, depending on who the examiner is, it often depends whether you get stellar nebula or giant molecular cloud. So make sure you know both those names. Stars are born in these. Gravity, there's gravity again, acts on the dust and gas in the nebula. A large amount of mass will form a giant star, a smaller amount of sun-sized star, or an even smaller star. So it's how much you start off with and how much gets compressed to actually form the star. Stellar nebula are vast. Stars are much smaller and come from the collapse only of part of the nebula. So that left-hand tower, can you see sort of what looks like almost like the ear of a dog up the top? That apparently is budding off a new star. So you can see that probably only a very small amount of that actual nebula has gone into the making. And these are vast. These are like sort of light years tall, these things here. These huge, this Eagle Nebula has got these really tall things. Okay, so, right, the birth of stars. There are 3 to 4 main stages in the birth of stars. There's the nebula. We've done that. Proto-Star Formation. Pre-main sequence formation is not always mentioned, but that's the stage just before it actually starts fusing hydrogen to helium. And then you get main sequence formation. So this is the birth of stars. These 3 to 4 stages. I've just seen it as 3 stages in some places and 4 stages in others. That's why I'm doing it as that. Right. So the action of gravity, the increase of density, and energy changes are all very important processes. So first of all, the nebula collapses and forms clump. And as these clumps get bigger and bigger, more matter is drawn in because of gravity. These particles also rub together and generate heat through friction, forming a protostar. Okay, the next one. So this is in more detail. As it gravity collapses, and I always used to teach this as remember the C's. Gravity causes collapse, contraction, and compression of the dust and the gas. This causes collision, another C, friction, and heating up of the particles, causing an increase in density. Gravitational potential energy, which is your collapse, is converted into kinetic and heat energy. And this starts to rotate, and this is a protostar. Notice it takes from 10,000 to 1 million years. Protostar to main sequence, that you carry on with all this collapsing and compression and contraction and this sort of thing, forming heat and light. The density of the star increases, heat is trapped, and the protostar, which can be quite kind of see-through at first, transparent, eventually becomes opaque, weakly radiating heat and light. A protostar with all its mass just before fusion starts that's a pre-main sequence star. And then it becomes a main sequence star because the matter becomes hot enough so that thermonuclear reactions start. If you just learn that page, you're probably actually enough for the birth of the star. Okay, so there's your new main star. I've pretty well talked about that. The Protostar becomes a stable main sequence star. It will be this until hydrogen runs out, which is about 1 million to several billion years. 1 million is if you're kind of a huge, enormous blue star. Billions of years is your red star down the other end of the HR diagram. And here also is a good summary. So the yellow is showing the collapse, contraction, collision. F is in red because friction causes heat. Density increases, and then eventually the gravitational potential has conversion to thermal heat and light and other radiant energy. Heat is trapped because density has increased. So notice that the main sequence star, it's getting smaller all the time, but it's more compact and much, much hotter. Now, this is it's the best analogy I could think of for the students that I would teach, is that a protostar is radiating heat, much like a fire or heater might, or you set an open fire going in a brazier at the beach or something like that. That is a bit like a protostar. This is just a rough analogy. But when a thermonuclear reaction starts, a vast amount of heat is given out. And if you've ever seen a picture of a nuclear bomb go off, that sort of amount of energy is what you're talking about. It's fusion reaction rather than fission, but it's still got a vast amount of heat. So just be aware of that incredible difference between a protostar and a main sequence star in terms of what's going on inside it and the amount of heat and light that's released. Now, at the same time as the star is being formed, you are often getting a protoplanetary disk from which the planets will form. And so the protostar is a central core, and there's a surrounding, rotating, flattened disk of dust. Notice that it is a disk, which means all the planets, not the dwarf planets, but the planets, all get formed along this kind of disk, which means they're all on the ecliptic. Central cores become the star, protoplanet eventually becomes planets, moons, asteroids, comets, etc. And then these new main sequence stars are unstable, and this is just showing jets that come out of it. This is interest, really. And if you look at Matariki, it's got young, through a telescope, the young stars are surrounded by gas because they're young and they still haven't quite got all the gas that hasn't even been either swept away by maybe a stellar wind or has yet to be absorbed into the star. Mass is important, very important. We're going to go on to the life and death of stars now. Most massive stars have the shortest lives. Stars are 25 to 50 times over a million years. Our sun will live about 10 billion years. Stars less massive have even way longer lifespans. Right, now here's an important thing, or few things. All stars become main sequence stars after their birth, all of them except for the brown dwarfs. As they grow, as they grow older, their outer layers expand, but the core contracts and becomes hotter because you've got increased pressure and density in the core, right? Outer layers expanding, core is contracting. What after that depends on the original mass of the star. Now, I've talked about the mass of the star. This stuff in yellow here on this page, bottom of the page, is now talking about the mass of the core of the star, right? If the mass of the core of the star at the end of the main sequence stage is less than 1.4, you will get a white dwarf. If the mass of the core is greater than 1.4, the star becomes a supernova, and then you get a neutron star or a black hole. And that's all to do with the mass, is all to do is just how hot the core can get. And a sun sort of sized star, or maybe slightly bigger than a sun sized star, is never going to go supernova because the core just can't get hot enough to start burning carbon. Okay, so, and here we are. Here's the main sorts of stars, and this is what happened. I haven't got brown dwarf on there, but that's mentioned before. So that's an important table. It's really good, actually, to rote learn the sequences. So rote learn the birth of stars. So Nebula, Protostar, pre-main sequence if you want to, main sequence star, red giant, planetary nebula, white dwarf, black dwarf. That's the sun-sized star. Just rote learn that. And then, again, when you get to the question, make sure you identify the type of star they are wanting you to write an answer about. Because, again, I've seen sun stars written about when they've clearly asked about a giant star and vice versa. Make sure you identify the star properly. And then if you've learnt the 4 stages of the birth of stars, and then you've tacked on main sequence, and then what happens after that, then just put that down. Just at the beginning of your notes, just beginning of where you're going to put your answer is fine. So you've got the sequence, and all you have to do is describe the different stages and then link them, show how that you actually go from one stage to the next stage. Because this is a continuous process. We teach it to you in a section here, a section there, and a section there. But it is actually a continuous process. And you got the idea of that with the birth of the stars, where there was continued kind of collapse and contraction and increase in density in the core of the star. You got that sense of a sequence. So you need to also have that sense of a sequence with this kind of main sequence death of the star stage. So here's the 2 stages. Here's a summary here. And also, because it's got different people understand different diagrams separately, this is other one I thought gave a better sense of scale in some cases. Obviously, the scale is not perfect. Remember that it's got 2 parts, a very hot, dense core, and we're going to be talking far more about the core now. It contracts an outer gaseous shell. Okay, now red dwarfs is just a very simple 1 page about red dwarfs, and when they've finished burning their hydrogen to helium, there's not enough.
Quick question, Jenny,
yeah?
Someone asked, is it possible for a neutron star to form, and due to the increase in density, neutrinos, it will collapse again to form a black hole?
No, because it comes from a star that isn't big enough. It can only form a neutron star. Why don't I discuss that when I get onto giant stars?
Cool.
Okay, I'll answer that. Okay, so here's a red dwarf. It just burns hydrogen to helium. It hasn't got enough mass in the core to ignite to get helium going, so it goes to become a white dwarf and then a black dwarf. That's pretty simple. Sun-sized star, this is the range of solar mass, and notice I've got mass of the whole star, not just the core, right? Sun-sized stars, there's just the relative parts of those 2 diagrams I showed you before, and I quite like this analogy with a sun-sized star, okay, which is just a bit of a joke. Main sequence star, and of course our star is in the main sequence stage, thank goodness, because it's going to stretch out to Jupiter when it becomes a red star. Now, what happens is the star is getting bigger and the core is getting hotter. Finally, it runs out of hydrogen. The mass of the core is less than 1.4 masses of the sun. So, therefore, the star goes on to become a red giant. Not a supergiant, not a red supergiant, but a red giant. Make sure you know where that is on the HR diagram. Now what you get is when it becomes to go from the main sequence star to a red giant, the core contracts, gets hotter, red giant forms, start fusing hydrogen to carbon and oxygen. Helium becomes a fuel. Now notice the outer layers expand and cool. The star is red because of coolness, but it's very luminous because of its size. So it's up near the top of the HR diagram, but to the right. So it's red in colour, low in temperature, but its luminosity, because it's so big, is still quite high. Okay, red giant to planetary nebula. What's happening is the core increasing, the outside is expanding until it literally starts to float away into the ether, into the universe, as it were. And then what you get is just the core of it, which gets even smaller and denser and hotter. The outer layers cool and drift away, and you get beautiful planetary nebula. And if you look at pictures online or in some of the main PowerPoints I've given you to look at, you'll see pictures of them. So red giant to planetary nebula, I've explained. When the helium, note though, when the helium has all become carbon, or carbon and oxygen, but we're talking about carbon here, the core becomes stable because the core isn't big enough to compress carbon and to start using that as a nuclear fuel. So therefore, it can't go any further. It doesn't, and what you end up with is a white dwarf. And the white dwarf is very hot. It's on the bottom of the HR diagram, but it's towards the left because it's got a high temperature, but it's not very big, so it hasn't got a very high luminosity. This carbon remains incredibly hot, so the white dwarf just radiates heat for goodness knows how many million years until it becomes just a cold lump of carbon. And then there is planetary nebula to white dwarf explained further. And that also explains why the red giant is in the part of the HR diagram it is, and why the white dwarf is in the part of the diagram it is. And you may get a question that asks that, or you may get a question that asks you to describe the difference between a red giant and a red dwarf star that's on the main sequence. So you need to be able to know your HR diagram well and be able to describe why a main sequence star is red, a red dwarf is red, and down the bottom of and why it's so cool and has got low luminosity, and why a red giant has actually got high luminosity even though it's a cool temperature. Those are things that you need to know. Okay, and so this is further explaining these types of stars on the HR diagram. So just make sure you read through these. This is pretty well saying what I've done before. Now here's Sirius A and Sirius B. There was a question on this one time. And Sirius B is a white dwarf, and you can see it right down the bottom in that kind of left-hand bottom shaft of light. You can actually see Sirius B. Okay, and sometimes a white dwarf might have some extra hydrogen, which causes an explosion, and you get a nova. It's nowhere near as bright as a supernova. It's only, it only flares up for a bit, and it's nothing like what a supernova would look like. Okay, now giant stars. We're on to giant stars now. Now notice that we'll look at this, the person who was asking the question before, we'll look at this with this. You can get massive star and then supermassive stars. And massive stars, they're big enough for the core to collapse and form a neutron star, but they don't start enough from like a supermassive star, which actually collapse beyond what a neutron star has. So I think we can all imagine a neutron star collapses. I'm going to explain that when I actually get to neutron stars. Sorry, I'll answer it properly when I actually get to that. Okay, so the life cycles of giant stars, that's another one. And it actually shows Betelgeuse. And sorry, I haven't got the arrows. A giant red star. Oh, yes, you can actually see the picture. It's the one on the bottom right. It's not showing red, and it's in Orion. It's not showing red in the actual constellation. But when you look at it in the sky, you can see it. Okay, when huge stars with giant masses get old, they become enormous supergiants. So what they've done is they've burnt hydrogen to helium. Then the similar thing happens. The outside expands, except much, much bigger. The core compresses, except much, much more. So they become supergiants. And, of course, they are bigger in size. They're not more massive, of course, because they've burnt a whole lot of their mass, but they are bigger. And so it's important to also, back in the sun-sized star and here, to realise the difference between a star being bigger and being more massive, right? And so a red giant is bigger, but it's not more massive than its original sun-sized star because a lot of the mass has been fused as fuel. Okay, so these are able to burn helium then to carbon, and then the core is hot enough inside, and it keeps on contracting to actually burn carbon to other elements as well. And so this is very similar to the diagram before, except it's becoming a supergiant, and it tends to be more of an orange colour, so it's a little bit warmer than the red giants. And the super red giant, what happens in the core, and this is blown up, but the if you've got this textbook, the diagram in that is quite good, and I can't remember exactly the page of it. Oh, it's just here. It's actually on 208, and it actually shows the page better. Oh, you probably can't see it, actually. I just realised because I'm sharing my screen. But it is page 208 in the new edition of the Level 2 book. And that expanded where it's got iron and the silicon, oxygen, carbon, helium, hydrogen. That's actually showing the size of the core. Actually, that is much, much smaller. And I think the next diagram, no, I haven't got that diagram here. That's actually, if you shrink it down to the size of the core in the diagram, those happen, that the core is collapsing, is getting smaller all the time. So hydrogen, helium might start off as that big, but then the helium to carbon is smaller and the carbon to oxygen is smaller, and until you get a very incredibly small, dense core, but made completely of iron, which can't be fused to anything else. And just in case you're interested, it shows that the time that the core is in those various stages gets less and less. Okay, the collapse of the core is that iron atoms don't fuse to make heavier elements, so the outer layers of this giant star collapse towards the centre of the star. It happens very, very quickly. During that collapse, the nuclear and the outer parts of the star are pushed close together. So elements heavier than ions are formed. And also, when you get a supernova, it is so hot in the supernova that you also get the other big elements. So the great big heavy elements like uranium and stuff like that are all made in supernova. So when they say that we are made of stardust, because this actually, a supernova explodes and the dust becomes part of a nebula, and of course, which then forms stars, then forms planets, then forms life. And so the expression that we are made of stardust is actually surprisingly an accurate one. Okay, and there's a supernova. That's what the star was like before, the right-hand one, and that's what it looked like in 1987. And then when they last looked at it, there was a neutron star forming in the middle. So obviously that's the right-hand picture is not to scale compared with the supernova. That neutron star would probably be even smaller than what the arrow is pointing to in that middle picture. And again, for interest, if you're interested where all the elements have come from, this is a really cool periodic table that tells it to you, but I'm not going to spend time on it now. After the supernova, if the star's remaining mass is about 10 times the mass of the sun, it will collapse into a small, dense neutron star, which starts spinning. And a neutron star forms literally, you know how when you've got the atom, there's a gap between the neutrons and the protons and the electrons. Well, the electrons effectively get squashed down and towards, combine with the protons, and you get neutrons. So it's like if you squashed your body down and got rid of all the gaps between the electrons and the neutrons and protons, you would be teeny, teeny, tiny. Okay, but quite a lot of mass. And that's what happens with a neutron star, but there's not enough mass in that core to make it go any further. the absolute supermassive stars, they collapse far enough to probably go past the neutron star, and it's very hard to conceive of what happens after that, but it goes beyond the total squashing of the atom to something even again, and that's the black hole. Incredibly dense, with a gravitational field so strong that even light cannot escape. And there's a neutron star and pulsar, and neutron stars can start spinning, and they're pulsars, and they can be picked up. They're very regular. They've got a very regular spin. And there's a comment on black holes. And this is exactly what I had before, where these stars are on the HR diagram. And please notice that neutron stars and black holes are not on the HR diagram because they have no luminosity. And brown dwarfs, found below and slightly to the right of red dwarfs. Okay, the last bit, formation of planets and moons. And as I said, this is often I've marked papers and found that the HR question and the stars ones are done well, and for some reason the planetary stuff isn't. And I suspect it's because it's often done near the end of a topic, and teachers run out of time. But anyway, our solar system formed 4.5 billion years ago. In the resources, you will actually find.
A quick question, Jenny. Someone asked, does a neutron star do anything after supernova? Does it just die?
No, it can start spinning and become a pulsar.
Cool.
Yeah, and to tell the truth, I'm not too sure whether it dies or not after that. I'm not too sure. That might be something interesting to Google once I get off. Yeah. Sorry about that. I would say that its life would be measured certainly in millions of years rather than short, and perhaps billions of years. Okay, solar system forming. And again, you start with a nebula, and if you remember, you get the protostar and you get a protoplanetary disc, which is kind of flat and spreads out. And you can see that in the diagram that way. And notice that other solar systems consisting of a star and exoplanets also form this way. This is the dominant theory of how the solar system forms. There are one or two other ideas, but this is the one we teach. And so, again, there's a stellar nebula. It's showing a protostar, but this time with a surrounding disk. And this actually shows protoplanetary disks around protostars in Orion, in the Orion Nebula. So, excuse me again, I've been talking far longer than I usually these days. I'm out of practicing, I'm not. Okay, proto-sun becomes hot and dense enough for nucleus fusion to be started. Sun was born. Obviously, the protoplanetary disk is not only made of gas, but there's a lot of dust. These start to clump together, and I like that word clump. There's a proper word which I'll go into in a minute called accretion, but you do get them clumping together to form planetesimals. And then when they get to a certain size, they start to attract each other through gravity, and you can accumulate enough matter to form a planet. This takes about 10 million years. And this also gives you shows a good diagram. There are a lot of collisions went on in the early history of the solar system, and that's showing you that in there too. And this is, the disk is apparently kind of, it expands going out from the star, and this is actually showing the different stages: disk formation, sedimentation, planetesimals, solid stars forming, which are Mercury, Venus, Earth, Mars, and then the gaseous planets forming. And what's important here, temperature becomes important here. The disk is hottest close to the proto-sun and then the sun, and gets cooler at the edge of the disk. And this affects how the planets are made. And so close to the sun, it's about 2,000 Kelvin, and then out to sort of about 100 Kelvin, which is quite cold. This affects whether a new planet is a small rocky planet or a larger gaseous one. So this is an important concept to learn, slide to learn. The frost line is the temperature that separates the formation of rocky planets from gaseous planets. And the frost line is between Mars and Jupiter. And it's talking about accreting planetesimals, and this is accretion means the condensation of matter under the influence of gravity to form larger bodies such as planets. So you may get that word accreting, and if you're finding it a bit hard to get your head around that, then at least know what the process is, because you don't lose a grade because if you've explained what a process is well and you haven't got some long fancy word, then you generally don't get penalised for it. Okay, so this also is showing more what happens. So inside the frost line, rocks and metals condense, hydrogen stays gaseous, and hydrogen is and helium is actually swept out past the frost line. Ice condenses onto rock outside the frost line to form the gaseous outer planet. So there is some rock that would still condense, but particularly ice is condensing as well. And these planets that are actually these, so that I go over this a bit more in a minute. Sorry for sort of burbling a bit right now. But the rocky planets which are inside the frost line form first, and they are mostly rocks and metals, which need the warmer temperature to be able to kind of be warm enough to sort of condense and that. And then outside of that, you've got the ice forming and large planets forming, which are able to gravitationally attract and hold on to hydrogen and helium. Okay, and this is kind of explaining what happens. And when actually you finally get the star, you get a lot of radiation coming out of the star. That blows the rest of the dust away so that you can start to actually see new planets. And a lot of that dust and stuff that gets blown away, some of that ends up forming what's called like the dwarf planets that are further out in the Kuiper Belt. And also there's a little bit I'm going to tell you about in asteroids, to do with asteroids in a minute. So it seems like the objects in the Kuiper Belt and the Oort clouds are remnants from the formation of the solar system. Okay, there's a bit about the asteroid belt, and one hypothesis is that it's a planet that wasn't quite able to clump together to accrete because the planetesimals couldn't accrete because the gravity of Jupiter prevented it. There may be other reasons as well. And there's the Kuiper Belt and the Oort cloud, which are way out beyond our solar system. Okay, inner rocky planets, small solid surfaces, rotate slowly, have few or no moons. And here's how they form. They're attracted to each other by gravity. You get a round molten sphere. The denser material goes in, like that iron is the inside out in the middle of our planet. You get a crust forming on the outside. You get outgassing and volcanoes, like our planet had a whole lot of volcanoes. That makes gas come out and some water. You also get a lot of bombardment from other bits of planetesimals and bits of rock that are around. And you can still see those craters visible on the surface of the Moon and Mercury. Also, atmospheres form around planets that have got enough gravity to hold on to them, and Earth is big enough to have a decent-sized atmosphere so that eventually you could have oxygen in the atmosphere and you could have us. Summary of the formation of rocky planets, it's pretty much what I've actually gone over just now. Outer gaseous planets, they're much larger, rotate very quickly, mostly made of hydrogen and helium, and also something I should have put in there, which I might put after this, is that Uranus and Neptune have got quite a lot of water and ice, watery ice on the surface. And this is how they formed. There's more ice and gas because they're formed outside the frost line. They still have anything metallic and rock or anything rocky going into the core, and then they've got gases around them and dust. And there's a summary of that too. Late bombardment is what I was talking about, and you don't get many planets on craters on Earth that you can easily see, but this was one formed in Arizona 50,000 years ago. Now, this is an important thing. Some of you may not be able to get your head around this, but sometimes it gets occasionally asked. Gravity in the massive planets. Obviously, our planet Earth, you would think that Jupiter would have been so much bigger, would have so much more gravity than us, relatively, but in actual fact it doesn't, because it is all to do with the centre of mass on the planet and the distance from the centre of mass and the radius. And this explains it here. If the gravity of an Earth-sized planet is relatively strong because surface objects are nearer to the centre of the mass of the planet because of the relatively small diameter and radius. Jupiter-sized planets are more massive, but the surface is further away, which means the force of gravity is weakened at the surface. So the gravitational pull is only 2 to 3 times the Earth, when you'd think it would be much more, but it's not. Only some moons around. There's about 146. I can go on a couple of minutes more, can't I, Andrew? Is that okay? Andrew?
Yeah, that's fine.
Yeah.
And we'll post the PowerPoint at the end of this. We'll just put it in the comments.
Yeah. Okay, so 146 moons. There's some being discovered around dwarf planets. I'll go quickly into the how they are formed. Only larger moons around. Smaller ones have highly irregular shapes. All moons start as lumpy planetesimals and keep on accreting more matter. If they get big enough to be round enough, they will be a round moon. And if they're not, they stay lumpy. All planets have to be round to be a planet, but moons don't have to be round to be a moon. And remember, of course, that a planet is what orbits a sun or a star, and a moon is what orbits a planet. Okay, 3 ways in which moons have formed: by collision, e.g. the Moon and Pluto's moon Charon. Both moons are large relative to their planets and are the only solar system objects we know where the moons are large relative to their planets. You can also get moons formed from a circumplanetary disk. If you remember before, we had a protoplanetary disk around a star. You can also have a disk around a large planet, large moon, like the larger moons of gaseous planets. And then you can literally get captured asteroids. Okay, so here's the one hypothesis of the formation of the moon, and the one we tend to teach, where there was a smaller planet called Theia, which crashed into the Earth, spat out a whole lot of stuff which formed our moon, incidentally also made the size of our planet big enough to actually, so we could have an atmosphere that was enough for life, and also put more molten material into the centre, so we have a magnetic field, which means that so harmful cosmic rays are deflected away from our planet most of the time, and also possibly also help towards tectonic plate movement too. Okay, and there's a good diagram of it. Larger moons of gaseous planet, and particularly Jupiter shows this, would have been formed from a circumplanetary disk, and the moons close to Jupiter are dense and rocky, and further out are less dense and have more ice, except for Io, of course. And that just explains that a bit better. And here we have these kind of 4 planets inside, which are kind of equivalent to our 4 moons, which are sort of similar to in formation to our rocky planets, and then these outer ones, which are the Galileo moons, which are the ones we always see under telescopes. And then here is possibly one way how Mars ended up actually getting 2 asteroids as moons. The moons actually always rotate around the planet a different way to the moons, the other moons that always rotate the same way as the planet's rotating, but these moons rotate the other way. Neptune's largest moon is quite possibly a captured Kuiper Belt object. See, KBO stands for Kuiper Belt object. And you can still get impacts happening. This moon, Mimas, shows a crater, and also Uranus was actually knocked off kilter, so it actually rotates kind of on its side compared to us. Okay, and that just shows other stars with exoplanets. And there's a little bit at the end about centre of gravity between moon and planet, which I'm not going to go over, but you can certainly study. I don't know whether you'd get a question on this, but again, if you're going for excellence, then find out this. So, I mean, it's a bit like a seesaw. Rotation, if the centre of gravity is in the middle, common centre of gravity when they rotate. If it's a bit off kilter, they still orbit a common centre of gravity, and then you get what happens. They don't all rotate, sorry. Okay, so that's something that's an extension part. Right. So stop sharing now, Andrew. Is that it?
Yep. We'll stop the sharing. I assume Doug's on the other line to close the stream.
Yep, that's correct.
Thanks to everyone who joined in or is going to be watching this, and I hope it's useful. And I think you all have the link for the resources that are online, but maybe Andrew or Doug will talk more about that. Okay.
Brilliant. Thank you very much, Jenny. Really appreciate your time and your effort again in preparing that wonderful presentation and our trip through Earth and space science. It's great to see some questions from people. Andrew, were there any that needed to be answered at the end?
No, I answered all the ones that throughout. It's just we'll post the PowerPoints in the comment section at the end of this.
Awesome. Oh, well, thank you so much, Jenny. Really appreciate that. And there's certainly, hopefully, going to be useful to students in the future as well. Have a great day.
Yeah. Now, do I need to do anything about these PowerPoints? Have you effectively got them now, have you?